No questions? All right, today we're doing experiment 17. We're going to break it up into parts. So the first part is electrolyte properties. And so we got to talk about water first. Water is the first thing we're going to test. So H2O liquid. And so what's the difference between distilled water and deionized water? Well, it's a process of purification, and they aren't the same thing. Distilled water is actually more expensive because it costs more energy to purify water that way. But it should be pure water. And so if we have pure water, what is in pure water? H2O molecules. You have H2O molecules in there, but let's take a closer look at a sample of water. So if we have a sample of water, like in the bottle here, and we try to see, of course the H2O molecules are extremely small. Extremely small. And we can't see them, but we know that they're there. And so we're going to have H2O molecules, but if we could see them, what are they doing? What are these H2O molecules doing? Well, this is at room temperature, and they're going to be moving around. They aren't just fixed in one position. And liquids, we know are going to have certain types of motion, but let's just look at motion in general. So we have kinetic energy. Kinetic, do you know what kinetic means? Motion. And so this is the energy of motion. But if you think about motion, there's so many different ways things can move that it seems like there's an infinite number of possibilities, but what we do is we break it down into basic types of motion. And the basic types of motion that we have are going to be translational motion. Translational motion, it moves from point x1 to point x2, let's say, or y1 to y2, or whatever, anywhere in the three-dimensional coordinate system. So we have translational motion. It's one possibility. What's another type of motion that's encountered? There's something called vibrational motion. If we look at the water molecules themselves, the atoms can vibrate with respect to each other. And so the hydrogen-oxygen bond can squeeze in and squeeze out, so it can vibrate like this. They can scissor in and out like this. There's different types of vibrations that you'll encounter just based on the molecular structure. And then there's one more type of motion we would see, and that would be rotational motion. And so what we have in this water sample is we're going to have water molecules that are vibrating, rotating, and translating. Now, this water is at 25 degrees C. If I take a thermometer and I measure let's say it is at 25. I don't know what room temperature is today, but if I measure anywhere in this water, it's going to be the same temperature, room temperature. And so does that mean that, no, actually, we use rotation here. Vibrations would be something like this, Does that mean that all the water molecules have the same energy, the exact same energy? Yes? Well, anywhere I put the thermometer, what's important about the thermometer is this. The temperature is related to the kinetic energy. In fact, the temperature is directly proportional to the kinetic energy. The kinetic energy, Petrucci uses this symbol, this lowercase e sub k. That stands for kinetic energy. And if the temperature anywhere in this liquid water is 25 degrees C, does that mean that all the water molecules have the same kinetic energy? No. You know that the temperature is, actually, it's not here. You know, when we think about temperature, we think about the constant times the average kinetic energy. And so we look at the collection of water molecules here and figure out what is the average kinetic energy of this. And we come up with what we call a distribution of energies. And this distribution of energies will have a characteristic shape to it. And so if we make a plot, on the y-axis we'll plot out population or number. And on the x-axis we'll plot out the kinetic energy. What we'll see is at 25 degrees C, the population is going to show a distribution like this. You know, it kind of looks like a normal or a Bell or a Gaussian type distribution, a normal bell-shaped curve. But there's a tail here on the high energy side. This distribution is not called a normal or bell-shaped curve distribution. This is called a thermal distribution or a Maxwell-Boltzmann distribution. This is a kinetic energy distribution is what we have. Kinetic energy distribution. When we look at the average kinetic energy is going to be somewhere here. You know, the highest population of water molecules will have this energy here. And then some water molecules will have low energy, some will have high energy, you know, in this population. And so we could just map that out. The average E bar is here. So what happens if we change the temperature? If we change the temperature, we go to higher temperatures. What we do is we lower the population of lower energy and increase the population of higher energy. So let's say we still have the same total population. And so the area of the curve would have to be, area under the curve would have to be the same in both of these. So it kind of flattens out a little bit. And so this would be at, you know, at increased temperature. So the population of higher energy increases. At lower temperatures, you know, the population of lower energy water molecules increases. The population of higher energy water molecules decreases. And so the average kinetic energy drops. The average kinetic energy here is offset because of this higher energy tail to it. And so this would be the average kinetic energy at decreased temperatures. So when we look at the when we look at this for water, you know, at 25 degrees C at room temperature, we're going to see some population distribution that looks like this. We see that there are going to be some lower energy ones. Most of the water molecules will have an energy around here. Some will have the average around here. And then there's going to be a small population of water molecules which will have fairly high kinetic energy out here, the label red. And so this is a simplified kinetic energy distribution. The funny thing about this is, you know, when we think about kinetic energy, we normally think of it as occurring as a continuum of energies. A continuum of energies means that, you know, any energy is allowed. So if you're driving your car, you know, can you go any speed up to the maximum speed of the car? You know, are there any speeds that are forbidden by the car itself? No, you could go any speed you want, right? Well, that's like translational kinetic energy. Translational, yeah, these molecules can translate any speed they want, you know. There's no forbidden. So it could be moving fast, it could be moving slow, or anything between. But the interesting thing about vibrations is not every vibration is allowed. And it turns out there are only 3 vibrations that are allowed in a water molecule. you know. And so each of those vibrations occurs at a different energy. And those are allowed energies of vibration for a molecule, but, you know, there are forbidden energies as well. And the same thing with rotations. There are allowed energies for rotations and forbidden. And it's just because of the way it vibrates and the way it rotates, you know. It doesn't just vibrate any old way, any of an infinite. No, there's fundamental vibrations. And so it turns out that those energies are what we call quantized, that meaning that, you know, they're allowed and forbidden. It's like mass. Remember when we were talking about mass? You know, if you weigh out some powder out on the balance here, it seems like you can get any amount you want, you know. Just put in a little bit more, take out a little bit. But in reality, mass is quantized. You just don't know that it's quantized because we never weigh out, you know, single atoms or few atoms or whatever else. Because once you get to the atomic level, then not every mass is allowed. You know, you can't weigh out a half an atom or a quarter of an atom out. And so that's going to change the look of this a little bit, but it's okay. We aren't going to worry about that. We're going to just deal with this this curve as is, and then we're going to pay particular attention to this because this is fairly high energy. High energy here. And so that means, you know, in this bottle of water, there are some water molecules that have fairly high energy. You know, this red zone here. Well, how much energy is that? Well, that turns out to be enough energy to break bonds. In a collision. Enough energy to break bonds. When we look at the total population here, you know, roughly this is going to be, you know, approximately 4 out of a billion. And so if we have a population of 1 billion water molecules, only about 4 will have this degree of energy. Well, if you get 2 of these water molecules that have this high energy and they collide with each other, bonds will break. Water bonds will break. The water breaks apart. Well, if the water breaks apart, it's not stable. And so what will happen is it will rapidly reform. That's option 1. Or 2, new bonds will form, creating new substances. And so in this case, if we get 2 of these high energy water molecules, we get an H2O liquid colliding with another H2O liquid, and everything's just right, then we can get a Bronsted acid-base reaction occurring here. You know, this water would be the base, this water would be the acid. So the base gains a proton, the acid loses a proton, and we form that hydronium and hydroxide. Is there a driving force for this reaction? Is there a driving force for this reaction? No, actually there's no driving force because in order to determine if there's a driving force, we have to imagine the reaction going backwards and then determine what is the acid going backwards. Well, what's the base? The base is hydroxide, isn't it? Well, you have to be aware because it's not always hydroxide. Hydroxide turns out to be amphoteric. And so in some unusual reactions, hydroxide can actually be the acid, not the base. And so don't get tricked into thinking that hydroxide is always a base. You know, it's like hydrogen peroxide. Hydrogen peroxide is a very powerful oxidizer, but hydrogen peroxide can go both ways. It can also be a reducer. And so if you have an oxidizer that's even more powerful than hydrogen peroxide, then hydrogen peroxide will or must act as a reducer in that particular case. And so the same thing here. We can't always assume that's a base because we've memorized hydroxide as a base. We have to look at the reaction. When we look at the reaction here, well, it is the base because it's donating, hydronium is donating, hydroxide is accepting. Anyway, hydronium can only be an acid. So is there a driving force? What is the driving force for this particular type of reaction? We go from less stable to, are we? Which is a more stable combination, water and water or hydronium and hydroxide? Water and water. And so there's no driving force because we're going from weaker to stronger. And so, normally we say that there is no reaction, right? That's not a driving force. Well, if that's not a driving force, then shouldn't we just say no reaction? Well, we'd like to say no reaction, but what happens is, can you stop the collisions from happening? No. You cannot stop the collisions from happening. The collisions are going to happen because the water's at 25 degrees C. The water's at 25 degrees C, there's going to be a small population of high-energy water molecules that are going to collide. The problem is they collide and they form this, hydronium and hydroxide. Hydronium and hydroxide are very unstable. That's a highly reactive mixture. And so if hydronium and hydroxide react with each other, it'll form two waters. And so there's a good driving force in the reverse direction. And so different ways we show that. One way we can show that is just no reaction. Another way we could do is by uneven arrows like this. But why uneven arrows? Well, this is what happens. Okay, immediately when we form hydronium and hydroxide, yes, those will likely react to go back to water. But once these have reacted, what's going to happen in the next instant of time? In the next instant of time, it'll reform. And so have you ever heard of a dynamic equilibrium? A dynamic equilibrium is where the rate in one direction exactly equals the rate in the opposite direction. And we reach something called a steady state. And so what's going to happen here is we're going to reach a dynamic equilibrium where we form it as fast as we consume it. And so that doesn't mean it's zero. That means there's going to be a steady concentration of hydronium and hydroxide in pure water. Because it's being formed like this, and it's being consumed like this, and then we end up with stable amounts. Even though it's constantly being formed and constantly being consumed. Do you know what that steady state is? That amount in pure water is? That amount in pure water turns out to be this. Pure water is not really pure. Do you know what pure water contains? Pure water contains naturally a hydronium ion concentration equal to 1.0 times 10 to the minus 7 molar. That's the steady state concentration. So yeah, the hydronium is reacting all the time, but it's being regenerated all the time as well. And so we've reached this point where as fast as we can react it, it's being regenerated and keeping or maintaining this concentration. This concentration is related to pH. pH is the power of the hydronium ion concentration. If we look at the power of the hydronium, it's 7. And so this is called pH 7. You get the right number of sig figs. It's 7.00. This is at 25 degrees C. Because if we change, actually I should just do it. If we change the temperature, do you know what happens? It doesn't matter. I could leave that. 2 sig figs is fine. You know what happens if we change the temperature? If I lower the temperature, will the pH change? If I raise the temperature, will the pH change? Yes. Yeah. Because if I raise the temperature, what's going to happen to the population here? It increases, meaning I'm going to generate more hydronium by having more collisions. Because the pH actually changes with temperature. But we know, we know pure water is what we call pH neutral. Why do we call pure water pH neutral? Because, yes, it's not because it doesn't have any hydronium. Hydronium is strong acid. It's because the hydronium and the hydroxide ion concentrations are equal. That's what we call pH neutral. The pH 7 is neutral. At a different temperature, is it still neutral? And so that's the tricky thing about pH, and it's something we'll talk about later. But what we do is we kind of adjust or normalize the pH. So if the temperature changes, we recalibrate everything so it still reads 7. Anyway, here. So in Chem 1A, normally we'd say NR here, no reaction. But the reason I'm bringing this up is that, you know, there's going to be a small population of ions here. And how significant is that? The same thing happens, you know, we come up with some kind of qualitative assessment, like for example, barium sulfate. Barium sulfate we say is soluble or insoluble? Barium sulfate's insoluble, but is it 100% insoluble? It turns out no. This is why you don't want to wash too much. If you wash your barium sulfate too much, you're going to lose some. Do you know why? Because if one of these high energy water molecules strikes the surface of barium sulfate and knocks ions off, then a little bit just dissolved. Right? And so the more water you wash it, well, the less barium sulfate you're going to get. Because a little bit will dissolve, no matter what you do. Well, the significance of this is because what we want to do today is we want to look at solution inventories, and then see, you know, if I have some pure water consists of mostly water molecules and a tiny bit of hydronium and hydroxide. Now, what do we call water? Should we call it a strong electrolyte? Weak electrolyte? No, we call it a non-electrolyte. We call it a non-electrolyte because the amount of hydronium and hydroxide here is minimal, minuscule, kind of negligible. It doesn't really react other than for pH. It doesn't really do anything because there's such a tiny amount. And so essentially it's a non. And here we could say no reaction, but if this was no reaction, then how do we get pH? You know? And so we have to account for that. Well, there's certain tests we're going to do today, and so today deals with, at least the first part of the lab today deals with electrolytes. And so let's talk about electrolytes. There are two definitions for electrolyte properties. What are the two definitions for electrolyte? High ionic conductivity? Yeah. High conductivity is one definition, but that's not the main definition we're going to use. What's our main definition we're going to use for this class?
If it dissociates into ion?
Yes, if it dissociates, the degree of dissociation, or not just dissociation, because we have one other process, hydrolysis, degree of hydrolysis. For example, did the waters really dissociate? Not, I guess maybe in a way yes, in a way no. This is a hydrolysis, right? And so that's our definition that we're going to use, this degree of dissociation with degree of hydrolysis. And we have this issue come up. The reason we need two definitions is this. Sodium chloride, salt, is that a strong electrolyte, weak electrolyte, and non-electrolyte? It's a strong electrolyte, right? And so, well, strong electrolytes should conduct electricity quite well, right? And so here, this is sodium chloride salt, right, which should conduct electricity quite well. Let's see, it does. You've probably seen this in Chem 4, I'm sure. This is just DI water. Just some DI water. Here. This is the light bulb apparatus. We have one electrode here, one electrode here. One of these electrodes is positive, the other electrode's negative, you know, has a charge buildup. but there's nothing connecting them. And so this is called a voltage. You know, when you build up positive charge on one, negative charge on the other, it's not stable. Voltages are not stable because, you know, both electrodes want to be balanced in terms of charge. But if there's nothing to conduct, you know, we've got excess electrons in one electrode, if there's nothing to conduct electricity to the other, then it's going to stay that way. Actually, let me talk one more thing. Chemists and physicists deal with two types of energy. There's kinetic energy, and what other type of energy is there? One other type of energy. Kinetic energy versus potential energy. Have you heard of potential energy? And so are these electrodes hot? No, these electrodes are room temperature. They aren't hot. And so they don't have high kinetic energy. But these electrodes right now have high potential energy, right? Very high potential energy, because you don't want to stick this into your bathtub, otherwise you'd electrocute yourself because of the high potential energy. Chemists are very interested in potential energy. For example, methane and oxygen. You know, if I bleed methane into this lab room, it's not at high kinetic energy, right? It's just at room temperature. Same thing with the oxygen in here, but that mixture of methane and oxygen has very high potential energy. Something bad can happen. And so same thing, these electrodes have very high potential energy, so I better be careful with this. Well, you know, one way to complete this circuit, this electric circuit, is to put some kind of conductor. So the conductor in this case will just be salt water. Let me see. And so, yeah, salt water is a strong electrolyte. Salt, I mean sodium chloride, dissociates pretty much completely, and it's a very good conductor of electricity. The reason why I say there's two definitions is because of this. Let's dump some of this out. And then I'm going to just put some salt. Now this is salt water too, right? Because I just put some salt water into here. And so this is salt water, but it's less concentrated. And so let's take a look. Would you say that's a strong electrolyte, weak electrolyte, or non-electrolyte based on the electrical conductivity? It looks like weak, right? And so does that mean sodium chloride is a weak electrolyte, or does that mean that sodium chloride is a strong electrolyte? Let's mix this up. The wires of that. And so that leads to some confusion. Therefore, we need two definitions for what an electrolyte is. One definition is based on electrical conductivity, because salt could be defined as a pretty weak electrolyte here, right? Sodium chloride is pretty weak because did it light up the bulbs? No. But when I was looking at it in the original, it was a strong electrolyte because it really lit up the bulbs, but it's the same thing. It's salt water. Salt water, salt water. Same thing, right? And so our two definitions, one is, again, electrical conductivity. The other is dissociation or hydrolysis. So which one are we going to use primarily? We're going to use dissociation and hydrolysis primarily. And the reason is because we aren't electrochemists, you know, right now. We aren't building batteries, you know. Electrochemists, they don't care. They don't care if it dissociates. They don't care about this or that. They just want it to conduct electricity well. And so what can conduct electricity well is a weak electrolyte. If you have a weak electrolyte and it's highly concentrated, that conducts electricity just as good as a strong electrolyte with low concentration, right? And so when we're thinking about conductivity, it's a different thing. But let's look at conductivity, since conductivity is part of this lab. Conductivity is going to be dependent on three things. It's going to be dependent on the charge. You know, we need some kind of charge carrier. An electron has a negative charge, a cation has a positive charge, and an anion has a negative charge. So we need some charge times a mobility. There has to be some mobility, otherwise we aren't going to get any kind of current flow, times number. And so the conductivity is usually given the symbol sigma, charge is given the symbol z, mobility is mu, and number is n. And so you don't have to memorize this equation or anything like that. So when we're looking at electrolyte properties based on electrical conductivity, we have to be careful about what? Concentration. Because concentration can fool us easily into thinking something's weak when we should have classified as strong. Or vice versa. So I'm going to get some water. What do you think is more pure, our DI water here or our distilled water? Which one is more expensive, DI water or distilled water? Distilled, because you have to boil it. It costs a lot of energy to boil water. And so I have a bottle of distilled water here. You buy it at the supermarket. It's not that expensive. It's going to be pure. So, distilled water, does it have charge carriers? Yes. It's got hydronium and hydroxide. So there's charge, plus and minus. Are these ions mobile? Yes. And therefore, distilled water should conduct electricity. So let's take a look at distilled water. Remember, everybody says keep the electrical appliances away from water, otherwise risk electrocution. Let's try the distilled water. And this is the electrodes are in the distilled water, but do you see any light? No. There's no light. Telling me that distilled water does not conduct electricity to any significant extent. In fact, you know, for the electrochemists who are interested in conductivity, you know, they don't care about anything. They just want to know how well it conducts electricity. Distilled water is classified as an insulator. Insulators have a certain conductivity below a set number or certain resistance above a set number. The set number is mega ohm resistance. Mega ohm resistance. And that makes water an insulator. So water is safe because it doesn't conduct electricity. Well, why doesn't it conduct electricity? Because water has these charge carriers. And yet it's called an insulator. How come? They're too few, right. The number, N, is so small that the conductivity is negligible. In fact, we call it a non-conductor. A non-conductor, in other words, we say that water is a non-electrolyte. Water is a non-electrolyte because the amount of hydrolysis is negligible. Okay. It's important for pH. You know, pH meters are going to require it, but for conductivity, it's so small. Okay. But water is, of course, very dangerous around electricity because we don't use distilled water for everything, do we? No. And sometimes we dissolve stuff in that water. But if we use tap water, does tap water conduct electricity? Yes. This bad connection. This wire. Does tap water conduct electricity? Yes, tap water does. And so you can see the bulbs are dimly lit. So tap water is a decent conductor of electricity. Does tap water taste salty? No, most of the time it doesn't. If you compare that to salt water tastes very salty. Did you see how bright the bulbs were with the salt water? That's because that was 1 molar sodium chloride. The molarity of the salts or minerals in tap water are small. And so they're dissolved minerals, which means that they're going to be ions in solution, which makes tap water a conductor of electricity. Okay. This is dangerous. Anything with high potential energy we have to treat with respect, otherwise it can electrocute myself or others. The same thing with chemical reactions. You know, any chemical reaction with potentially high potential energy we have to treat with respect, otherwise damage or injury could result. Okay, what's next on our electrolyte list? Oh, actually, before potassium chlorate, we need to do one other thing. What is it? Solid sodium chloride. Let's try that. When you buy sodium chloride from a manufacturer, it comes in a bottle like this. This is very expensive sodium chloride. Purity is fairly high, but not exceptionally high. This is like 99.5% or something like that pure. Maybe higher. So I have some solid sodium chloride in the beaker here, and so let's test its conductivity. Sodium chloride, solid, should be a good conductor of electricity. No. Solid sodium chloride is not a good conductor of electricity. Why? The ions are locked in place, exactly. The ions are locked in place. There's no mobility. If the mobility is 0, then the conductivity is going to be 0. And so how can we free up the ions? We could dissolve it. It's a strong electrolyte. It should dissociate into ions. This is like, how did we free up the sulfate in our unknown? Well, we dissolved it. And so let's just dissolve this. There we go. So add a little bit of water here. And you got it. And so now we have mobility. So it's a good conductor. But the same thing happens. I mean, if we make this overly dilute, you know, is it going to be a good conductor of electricity? No. And so in terms of electrical conduction, this is a weak electrolyte here. You know? In terms of our dissociation, well, it's a strong electrolyte. Which one are we going to use? Yeah, strong electrolyte. And so we got sodium ions and chloride ions, some mobility. Okay. All right, what's next? Potassium chlorate? Potassium chlorate we're going to do next time. Today, what we're going to do is we're going to break up the lab into parts, and we aren't going to do the parts in order. The next thing we're going to do is this. We're going to go to the reaction. So the first part is just to look at some electrolyte properties. The second part is to look at metathesis reactions, or double replacement reactions. And so let me do the first one for you, and then you'll do the rest. And what we're going to do is we're going to predict the products and driving force on paper first, and then I'm going to demo it and see, you know, did our predictions come out correct or not. And so what's the first two reagents we're mixing together? The first two compounds. Lead acetate? Lead 2 acetate or lead 4 acetate? What is it? Lead 2 acetate. So PbC2H3O2. 2. Lead 2 acetate, is it soluble in water or insoluble? It's soluble. And so I could write AQ here, or I could leave off the AQ. It's your choice. Plus sodium carbonate. Is sodium carbonate soluble or insoluble? Soluble. I want you to do all these reactions in your lab notebook. Okay, do them there. Leave yourself extra space for observations when we do the actual reaction. And so don't scrunch them all together. All right, this is just a double replacement reaction. AB plus CD yields what? Lead with carbonate. We get lead 2 carbonate plus sodium with acetate. I'm not going to balance this yet because before I balance it, I want to make sure there's a driving force. Otherwise, I can save myself some time. I mean, if there's no driving force, no reason to balance it. And so, do you see a driving force for this reaction? Well, what are the driving forces for double replacement? I'm sorry? Gas formation. Any gas? No gas. Precipitation. Any precipitates? Yes. Yeah, carbonates are soluble except for group 1 and ammonium. And so we have a driving force here. That's precipitation. The other driving force? Stronger to weaker acid. It just doesn't look like it's happening here. But anyway, we got a driving force, so this reaction should occur. And so what you're going to do is you're going to predict the products, determine if there's a driving force, and then balance it. So let's balance this. It's balanced. And then we're going to write the ionic equation and the net ionic equation. Well, some of the common errors here. Some of the common errors people will do AQ, and then they get tired. They get tired and they don't want to write one more AQ. And so they write these AQs and they think that's good enough. But is that good enough? No, it's not good enough because then I have to mark this one wrong because I don't know what you're talking about. You know, the solid, liquid, or gas, right? So that's a common error. So either write them for everything or leave them off for everything. Don't do halfway. Because usually when people do halfway, I think they're hedging, you know? It's like the people who give me 2 answers, you know, hoping one of them's right, and that I'll give them credit for that, but I don't. I pick the wrong one and do that. And so if you do that, then I'll... Well, anyway, then we go on to the ionic equation. With the ionic equation, what do? We ionize the strong what? Strong acids, strong bases, and insoluble salts, the strong electrolytes. So is this a strong acid? No. Strong base? No. But is this a soluble salt? Yes. And so we break it up or dissociate it into ions. So we get lead 2 plus 2 acetates. Common errors here is people don't write the charges. Or people don't balance it. You know, they just write 1 acetate rather than 2 acetates. It's common error. Sodium carbonate. Strong acid, strong base, or soluble salt? Soluble salt. And so this breaks up into 2 sodium ions plus 1 carbonate ion. Lead 2 carbonate. Insoluble salt, which means don't do anything to it, just leave as is. Sodium acetate, soluble salt, so we dissociate this. 2 sodiums plus 2 acetates. All right, this is the ionic equation is important, so don't X anything out here. You know, we see that acetate and sodiums are spectators here. But I don't want you to X them out because the ionic equation should stand alone. It's not some transition state between the complete equation and the net ionic equation. And so let's get rid of the spectators for the net ionic equation. We get lead 2 plus carbonate yields lead 2 carbonate solid. We're going to do this for each of the, 15 reactions I think we have? You know, don't write this on the report sheet. You'll see on the report sheet there's room to write these, you know. They give you a box for the observations. They give you 3 lines for the complete, the ionic, net ionic equations. I want you to do everything in your lab notebook. And this is the way the lab is going to work. You're going to write these. You can work with anybody you want. And this is going to be like science, because in science, do you know how people check their answers in science? You know how people check? They don't go to a book, the answer book, because there is no answer book to check. Do you know how people check their answers in science? Google? That reminds me of Yahoo Answers. This one's so funny. I think this guy was playing a cruel trick on it, but a lot of people voted it the best answer. It was just something way out there. And you don't know if they were serious or they were trying to play a joke. You know, but it was so far out there, I think they were trying to play a joke, but it got so many votes. The best answer. It's funny, it was nomenclature. Google, the problem with Google is it's not peer reviewed, you know? You know what peer review is? Peer review is you ask all your peers to review it to make sure it looks right, you know? You could do that here. We can do a peer review process. Make sure it looks okay to your peers. Maybe they can catch any mistakes. Right? And then what you're going to do is I'm going to check them off. I'm going to give you one chance to correct any mistakes. That is, if I find a mistake, I'll just X here. And then you get one chance to correct it. If you bring it back to me and I check it and it's still wrong, you get 0 points for this. If it's right, I'll give you 1 point for this. And so it's all or nothing, you know, for each reaction. And so you want to make sure you go through the peer review process quite thoroughly before bringing it up, because I will deduct for the most minor things, you know. A lot of people say, that's so, you know, I don't need this. Why do I need this charge here? It's obvious. Acetate is -1. I don't need, well, you know, I don't know you know that or not. You know? Or, you know, things like this, you know. Why do I need to tell you what the driving force is? It's obvious. It's that. Well, what is that, you know? Can you be more specific? Because if you aren't, I'm going to assume you don't know it. Remember, if you give me a choice, I'm going to assume you don't know, or I'm going to pick the wrong one. Okay? And so make it clear to me. You know, I know a lot of people don't want to write anything. You know, it could be simple things like writing the formula wrong, or etc. But, you know, after you're sure you have it right, bring it up and I'll check it once. If it's good, then you're done with that problem. If it's bad, you get one more chance. Okay. I mean, one chance, that is, the next time you bring it up, it's going to be 0 or 1. Okay? All right, that's it. Is it clear? There's a lot of confusion this morning, but is that clear? Okay.